this case right here, we say a of t is equal to 30 plus 2t. All right, that's 30 plus 2t. And that's equal to dv dt. I kind of just for the sake of this, I kind of go back to the derivation a little bit. And they put all the t's on one side and the dv's on the other side. So this would be 30 plus 2t dt is equal to dv, right? And then we integrate and we integrate. And this is going from 0 to t, and this is going from 0 to v. Okay, and so at this point, we just carry out those integrals. Right, and that just becomes 30t plus 2t squared over 2 is equal to v. So I carried out the integral on the left-hand side and the right-hand side, right? I was able to do that one in my head, but you don't have to do it in the head. If you have a calculator, you just plug that. I mean, it's a simple one, but you can just plug that integral into your calculator, put the bounds on it like that. The same one on the right, the other one's just gonna be v minus 0, so it's just v right there. And so this right now, we now have velocity as a function of time, just like that. Just by integrating, we get velocity as a function of time. Okay, so, bless you. So at this point, right, we look back up at the problem statement. It says that it's going to be doing this acceleration until it hits 400 meters per second. And so now I have its velocity as a function of time. I can figure out how much time it takes to get to 400 meters per second at this point, right? I just use that equation right there, right? So then I solve for, I set this equal to velocity of time equal to 400, and then I solve that. And then I end up getting t is equal to 10 seconds. Right, we just need that a little bit later. T is equal to 10 seconds. Right? What did I do to do that? I just plugged that in my calculator. And I would recommend doing that, right? I think even the TI-83 and 84 have solvers in them that do algebraic solvers, right? And so you're gonna have to be solving second order polynomial here, like a quadratic, and so then beep, 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 right? And then just plug it in there, let it do the work. You can start thinking about other things. You don't have to deal with it, and that's all the work I would want to see right there, right? You don't have to put anything else. You don't have to have all the algebraic steps and the quadratic equation and stuff like that. So t is equal to 10 seconds at this point, and the other thing I get is what velocity is a function of time, because I also need to know how far it's traveled, right? What's it asking? Then what find the total distance traveled. So I need to also figure out how much distance it's traveled as it's accelerating up to 400 meters per second, right? So then I come down and I say that the velocity is equal to dv. So that's how I get position is equal to dv ds. I got my velocity equation right there. So that's 30t plus 2t. Ooh, I'm just gonna get rid of the 2t squared. I'm just gonna call it t squared. 2t squared over 2 is just t squared. Oh, sorry, dv, I got an error right there. This is dv dt, not dv ds. ds dt. I wasn't done. That's the other joke I'll use a lot this message. I wasn't finished. I was just going to say, what have I done wrong here? It's perfect. I never make mistakes. It's all just planned out. I'm just trying to get you guys to find my errors. But that was tough. There was multiple errors right there. ds dt. Okay, so then I put the dt's on one side, and the s's on the other side, right there. And then I'm going to integrate this, and I'm going to integrate this. Okay. And let me put the bounds on this. This is going from 0 to 10 seconds. You could put that bound in there at this point because I solved right what that distance or what that time is. So I'm going to put that in straight into this thing right there as 10 seconds. So I can carry out that full integral there. And this is going from 0 to, I'll call that SF at the end of this. All right. And again, most of that could just be done with a calculator. And I get an SF is equal to SF is equal to 1833 meters. Right. These are just partial answers, right? That's just what's happening during the acceleration phase. And so that's pretty straightforward, right? Since it's a function of time, we just integrate with respect to time, right? We integrate the velocity to give us, or the acceleration to give us velocity, integrate the velocity to give us position, okay? And so there's the position right there, and we have that. Okay, cool. Any other errors that I've made in there? All right, so now let's talk about the decel. Right, the deceleration. So this now is an accel, which is a function of velocity. Right. Accel is a function of velocity. It tries to correct my spelling. This is notes program that I have, but I'm pretty sure it doesn't know what the hell I wrote right there. It does. Look at that. Look at that. It did. It guessed what I was trying to spell. Right? Acceleration, a function of velocity. Okay. So in this case, right, we're going to start out with this. There's two different ways to solve it at this point. Right. If you look back in our notes, when you're studying, you can look back at the notes. You'll see that there was a shortcut that it was associated with acceleration, function of velocity, and we could go right to having velocity as a function of position. And then we're going to use that little trick. We're going to use a chain rule to get there. And then the next page is, if you didn't know that trick, it's a little bit longer to solve it that way. Okay. So acceleration, function of velocity. This is equal to dv dt. And we'll do that chain rule. dv ds dt, where this is just the velocity, right? And so this is dv ds times v. And so I just put all the v's together, and I get ds is equal to v over acceleration as a function of velocity equation, dv. And it's okay to do this, right? And then we'll substitute in what the acceleration as a function of velocity is here. ds is equal to v over, and this is where you just put that equation, which we had over here, which is negative 0.003 v squared. dv, right? And I integrate. This is going from S1 to SF, and this is going from V1 to VF. Okay, so just carry out that integral just like that, right? So you just put just divide by the acceleration equation, just like that. And those are the same V's. This V right here, right, is the same as this V right here. So obviously that simplifies some, right? So at this point, right, we're gonna carry out the integrals. Let's put some bounds on this first. So this is going from one state to, from one state to another state. So it's going from 400 meters per second to 100 meters. It's decelerating, right? So we know some of these things. I know what the initial position is when this stage happens, right? This is gonna be what we solved before. This is 1833 meters. Is that right? Yeah. And then this right here is what I'm after. That final right there. V1, this is equal to 400 at the beginning of this state. And then this is going to be equal to 100 afterwards. Because remember, it's decelerating from 400 to 100. You could put in the definite parts of your integrals here, or you could solve for the equations and then put in your actual known values later after you get the equations. I just substituted in like this. And guess how I solved this? With my calculator, right? I used my calculator to solve this, right? did the left-hand side, then did the right-hand side, right? And what I got was SF is equal to 2295.1 meters. My boxing didn't work. Right, and if you don't know how to use your calculator to do these things, right, spend some time doing it, right? That's one way you could study. As you're working through your homework, kind of learn your calculator a little bit more. You get, again, it's a tool that you have, it's a tool that you get to use from here on out in your academic careers. You get to use it, learn how to use it. If you're like, where do I go to look? YouTube, right? You just YouTube, solving, doing integrals, YouTube, doing integrals on a TI-84, or doing integrals on a TI-89, right? And then some nerd out there has recorded a video of himself or herself doing integrals on a thing, and it'll help you out significantly, okay? Yeah, I also want to take a minute here just to say, hey, look, you see how shitty my handwriting is, right, as we go along. But this doesn't look so bad, right? Look, if you take a step back, you're like, oh, look at my solution. Easy to follow, understand, right? Like, I get what's happening. Maybe the minutia of some of those words are hard to read, but really, like, the math and the flow of it, and I boxed my answers and how I do it. So that's what you want to strive for this, right? Even if you have bad handwriting like me, most of you probably do, you could still have a nice, organized solution, okay? Yes, sir.
Is that SF the final distance?
Yeah, I probably should have called this S1, but yeah, that's the total, because I included this initial, it includes that initial displacement right there. So I put in the 1833 in that S1, right? You could treat them as two different problems and then just like logically just add them together afterwards if you want, but I lumped them together, right? So again, this was doing a shortcut. This went right to from acceleration straight to position, right? And you can't always do that, right? We were able to do it with this little trick using the chain rule. If you flip over to the next page, right? I think that this should be is this in your notes? This is in your skeleton notes. I did it the other way. So acceleration function of velocity is equal to dv dt, right? And then so I just put the dt on the left-hand side, I leave the dv on the right-hand side, but I divide by av. And so then I carry out this integral, right? I carry out this integral right here. I do my limits from 0 to t, and this is going from v naught to v. So this would be from, I think you could put in 400 to 100 at that point, okay? And you carry that thing out, and then, then at some point, actually, you can't do that. You can't put the bounds on that, because you actually need to get the velocity as a function of time first, because you need that to integrate to get displacements. And so at this point, you leave these things open, okay? Maybe you could put the 100 in there. But then anyways, we get to this. And this is what I mentioned before. I said you carry out the integrations, right? I carry out this integration, and then I get an equation like this. And then to get velocity as a function of time, at this point, I just solve for v. And that's, if you look back at your notes, that's how you said you did it. So you carry out the integration, and then you'll have v's on one side and t's on the other, and then you just solve for v. So I just plugged this in my calculator and said, hey, here's this equation. These two are equal to each other, solve for v, and this is what it gave me, okay? So that's just rearranging algebraically this equation. It gives me velocity as a function of time, okay? And then at that point, that's just equal to ds dt, and then once this is a function of time, which it is, right? There's a t down there at the bottom. Once it's a function of time, we just carry out that integral. We just carry out integration, and then we can get that same answer, okay? So again, just a little bit more steps involved that way, maybe a little more straightforward. If you don't see the trick, then you could do it this way as well. Okay. I just wanted to demonstrate that's, because I said it multiple times, just carry out the integration and solve for v. Like, what do you mean? Well, here you go, right? This little step right here. We carry out the integration and solve for v. Okay, let's go on to the next topic here, okay? Curved motion, right? Again, very systematically, we're gonna go through this, right? We're in kinematics of particles, and then we're gonna go to kinetics of particles later. And when we're in this kinematics, we're gonna do Cartesian coordinates, normal tangent, and polar coordinates. And then we're also gonna go on, when we do kinetics, we're gonna do the same thing, Cartesian, normal tangent, and polar coordinates. Okay, so it's kind of following a nice little path here. Okay. Let's get my right section of notes. Okay. We'll start with everybody's favorite, which is Cartesian coordinates, right? That's the one that's most innate to us. Okay. So here we go. So in this particular coordinate system, right, we have some sort of path. Right? This is a path that our particle is traveling along. And then we have a coordinate system set up, right, at some origin, and it has an x, y, and z axes, okay? And then we talk about position, right, is just going to be this vector r that points out to that position, okay? And a short time later, that position is going to change, and it's going to come over here. R of t plus delta t. And we kind of went through this definition of it earlier. So what we care about is the velocity, which is the change, time rate of change of what's happening with that position. Okay, and it's going to have multiple coordinates to it. Okay, so when we talk about velocity, right, the velocity is just the time rate of change of the position. So velocity is just equal to dr dt, right? The derivative of the position with respect to time. Right? It's just now that we got the vectors back in, we've got a bar over that to signify that there's a direction. Let me also write down what r is over here. R is going to have an x component in the I direction plus a y component in the j direction plus a z component in the k direction. Okay. There's a couple different ways you could do vectors, right? For the most part in this class, I'm gonna call them out with I, J's, and K's like this, right? You may remember in some of your math classes, you can also call it out as row or column vector. You call this X, Y, and Z, right? Or sometimes you call them a column vector instead of row vector. Seen those before. Sometimes it's nice. We'll kind of do it a little bit different. We'll kind of use them interchangeably, but a lot of times during derivations, it's nice to do the I, J's, and K's. Little hat on there. I hat, J hat, or caret, sometimes you hear that called, and K hat. These are base vectors. Right, they're unit vectors. Right. Direction, no magnitude. Okay. They have a direction but no magnitude. You guys remember that linear algebra stuff. Okay. So now it's come back down. So that's what my position is. And now if I'm going to take the derivative of that position with respect to time. So I just have to put in what I just wrote down for r in the r place down here in this definition. So this is going to be the derivative d of x in the I plus y in the j plus z in the k. The derivative of all of those with respect to time. Okay, now back to some calculus here. If you take the derivative of something multiplied by something else, so even though right, this is x in the I direction, it's actually x magnitude multiplied by the I direction. So if you take the derivative of something multiplied by something else, you have to use the product rule. You guys remember the product rule? You take the derivative of the first thing, and then you leave the second thing alone. Then you take the derivative of the second thing and leave the first thing alone. Yeah, you remember this, right? So we got to do that here to carry out this integral. So this would be dx dt in the I direction plus x times di dt. And so that's just that first term. That's this term right here, taking the derivative of x times I. Okay? So I took the derivative of the first thing, left the second thing alone, left the first thing alone, took the derivative of the second thing. And we just carry this out for all the other variables too. this would be plus dy dt in the j direction plus y times, bless you, dj dt plus dz dt in the k direction plus z times dk dt. Did the product rule all the way through. This time, there's nothing really exciting that happens here, right? Later on, when we do these other coordinate system, new terms are going to pop out. We're going to some things are going to come out of this. So but I'm just following the same procedure here. So, a couple things. This coordinate system over here, the x, y, z, this is the I, j, and k direction as they're sitting right here. Those things, no matter what that particle is doing along that path, no matter what it's doing, x, y, and z do not change, or I, j, and k do not change directions. They're all just sitting there. It's a fixed position. Later on, when we talk polar coordinates, our coordinate system is actually going to be moving. It's moving along with the particle. In this case, it's fixed over to the side. So if I'm looking at these derivatives, how is the I direction changing with respect to time? It is not. So that guy's going to 0. How is the j direction changing with respect to time? It's not. That's going to 0. How is the k changing? It's not. That's going to 0. Right? So all those terms are just going to 0 because our coordinate system is not changing. Right? And so what we're left with are just these terms. Right? We're just left with this guy, and this guy. Right? And that's what I've got drawn down here. Or written out down here. That's our big finding there. Right? So if I'm after my velocity vector, I just take the derivative of x with respect to time, that's in the I direction, the derivative of y with respect to time, that's in the j direction, the derivative of z in the with respect to time, and that's in the k direction. So this is called decoupled motion, right? So what's happening in the x does not affect what's happening in the y, which does not affect what's happening in the z direction. So they're all kind of independent of each other, right? I think you may have, you see, yeah, okay. We'll look at a video on Fridays. I always have YouTube Friday where we kind of look at videos related to this class, and this one we'll come to. There's a pretty classic thing about like if you're in a car and then if you like jump straight up in the air, then you'll land back in the car in the same spot because you're already traveling that direction, and then you're traveling in that direction is decoupled from you jumping up and down this direction. Kind of. I mean, if there's drag, that kind of throws things off as well. But if there's no drag, then theoretically it should do that. And I have this little cart thing that you could demonstrate too, where it like rolls along and it shoots a ball up and it lands back in the. Anyways, or if you another classic one would be like if you. This one always blew my mind. Like it only works if you're in a vacuum. But if you're in a vacuum and you like shoot a bullet like perfectly horizontal, and then you drop another bullet at the exact same time, they both hit the ground at the same amount of time, just completely different. Like one's like way down, miles away or whatever, and the other one just drops immediately. That's another classic example if it's decoupled. When you throw in drag and wind resistance, stuff like that, things get off. That doesn't necessarily work because the bullet can have some lift as it's going along and stuff. But theoretically, right, what's happening in the Y is decoupled from what's happening in the X, and so they'll do that. And then mathematically, we just showed that that's going to happen here as well. Okay. Similarly, you could do the same thing. I won't do that. We won't carry out the whole thing, but how you get accelerations, you can prove that these two are decoupled. Right? Say the acceleration is the derivative of the velocity with respect to time. In this case, now the velocity is dvx in the I plus vy in the j plus vz in the k. All that with respect to time. Right? And so if you did that, you would get this dv in the x, dt in the I, plus vx times di, dt, ... We won't keep going with it. But again, you'd apply that same concept, take the derivative of the first thing, leave the second thing alone, take the derivative of the second thing, leave the first thing alone. And again, what would happen is you'd have a bunch of derivatives of your coordinate system, and those all go to 0. And so you get the same result. You get this decoupled motion for accelerations. All kind of review, right? I mean, you've seen all this stuff before. Maybe just a little more formalized than what you've done before. And now our velocities and our accelerations can actually now be functions of velocity or functions of position. Like all the stuff we just learned about 1D, that could be happening here as well, right? You could even have acceleration in the x direction being a function of velocity, but acceleration in the other direction being a function of time, right? They're independent of each other. Okay. Cool. Pretty cool. Cool. All right. Right, so note decoupled motion is 3 1D problems. I've said that multiple times, right? A very classic example when you're talking about decoupled motion like this is projectile motion, right? And this is fun. These are fun. Projectile motions are fun, okay? So some assumptions when you do projectile motion, we always got to state them because there's some assumptions that happen here. We have constant gravity. For a typical problem, you have constant gravity. You don't always have it. When we talk about, we're gonna calculate orbital velocities a little bit later in the class, and when we do that, in that case, we do take into consideration the variation in gravity. But for now, constant gravity, because it is kind of a projectile motion. Things in orbit are. We're gonna neglect drag, right? No drag, and we're also gonna assume Earth is flat. It is not, though. Okay, just want to point. I just want to make it clear. The Earth is not flat. There's actually a pretty interesting documentary on Netflix about flat earthers. It's called Behind the Curve. It's pretty. It's very interesting actually, and if you should watch it. You should really watch it. It's actually really interesting, right? Because it really just shows their perspective and how they got there, and how it's actually a problem of ours as society of leaving those people behind, right? We somehow have left them behind in the and they're regressing, and they found each other. That's the other problem, is they found each other, and there's a community of them, and they're all feeding into it, and then but it's a growing community. It's a growing community. You could consider joining it if you wanted to. I don't know, but. One of the things at the very end, I'm not gonna give anything away. I will give it away. But there's a point at the end where the guys they come up with their own experiment, and they're like, oh hey, let's just get a flat lake, because it's gonna be flat, so it's gonna be flat, and we're gonna put somebody a couple miles away, right? And they're gonna be on the other end. It's gonna be at night, and we're gonna take this spotlight and we're gonna put it up at a certain height, and then we're gonna have on the other end a hole that's looking through it at at the same height. And so if you could see, there's a little hole over there. And so if it's perfect, like if it's flat, then you'd be able to see the light through that hole, right? You have to watch the movie. And then you do that. And then it's like, oh, perfect. And then they're like, oh, but so then they go, can you see so they get to the point, they do the experiment, like, can you see it? And they're like, we can't see it. But then if you raise it a little bit to account for the fact that the Earth is curved, then you can see it. And then if you see this, if you see it, yeah. And then at the end he goes, well, let me just raise it. And then he raises it, and then they can see the light. And then he goes, oh, would you? But see, even though he's proven it to himself that the Earth is round with his own experiment, I guarantee that they're gonna. And this is throughout the movie. They're like, well, clearly something must be wrong with our experiment, and there's some other factor that's causing this thing to happen. And the problem is, and the problem that they're having is they're coming into it with a preconceived outcome, right? Like we are going to prove that the Earth is flat, and no matter what, we're going to keep trying until we prove that the Earth is flat, as opposed to let's do some experiments and let the experiments lead us down the correct path. How science is supposed to be done. You're not supposed to go into it with a predisposed solution to it. You should watch it. That'd be a good activity on an evening like tonight. But anyways, we're going to pretend that the Earth is flat here. Especially in this class, when we get into it a little bit later, when we calculate orbital velocities, hopefully, like these things just go off in your head, like, oh my God, this is real. The Earth has to be round for these things to work, and all of it fits together. And okay, it's some interesting stuff. Okay, all right. So and the Earth is flat. We're gonna make that assumption. Okay, and then we're looking at the what's happening with these. Okay, so In this case, we have, so the way these projectile motion problems work is you start out with an initial velocity and initial angle is usually what you start out with, right? Initial velocity and initial angle. And we have assumed that there's gravity, right? There's gravity acting in the y direction. Right. Gravity's acting in the y direction, and then there is no acceleration in the x direction. This is what I said before, right? You can have two different things. In this case, we're gonna have acceleration. There is gonna be acceleration in the y direction, but not in the x direction, and that's okay, because we just treat these things separate, okay? So in the x direction, right, this is a constant acceleration. It just so happens to be 0. Right? X direction, we have constant acceleration. A is equal to 0. Right? And if you look up how we do those, right? V of x is just v naught in the x direction plus acceleration in the x direction times time. Right? For a constant acceleration problem, we look back in our solution method, that's what we came up with right there. In this case, this acceleration right here is 0, right? And then we can also calculate what v naught x is. That's just going to be v naught times cosine of theta. Okay. So then this is what my velocity is in the x direction. It's just constant, right? It's a constant velocity. It's whatever x component is of the initial velocity when it gets launched. That cosine theta just comes from this right here. Right? It's this component of it. I'm going to be doing lots of trig stuff in here, so hopefully you're good with that, right? All right, same thing with position. We had an equation before. X is a function of time, would be x naught plus v naught x times time plus 1/2 ax t squared. Again, that guy's 0. Right, x naught. In this particular case, x naught's equal to 0 as well. And so there's our position as a function of time in the x direction. It's just going to be v naught times cosine theta times time. Right? So just take velocity times the change in time, and it'll tell us where the positions are. Y direction, also a constant velocity, a constant acceleration rather. Constant acceleration, right? In this case, AY is equal to negative G. So VY is a function of time, again, constant. It's going to be V naught Y plus AY times T. Right? Now this V naught Y is just going to be V naught times sine of theta. It's the Y component of that initial velocity. All right, AY is just G, negative G even. And so this is what we get for our velocity in the Y direction, right? And it absolutely should be changing with respect to time, okay? Because there is some acceleration that's going down there, okay? And lastly, Y is a function of time equal to Y naught plus V naught Y times time plus 1/2 AY T squared. Y naught starts out as 0 in this particular case, and everything else I could substitute in, and this is what we get. Okay. And we'll do a couple problems in your home, probably next week's homework. I think this week's homework was just linear stuff, right? Guy that did it. What's his name? Yeah, it was just linear stuff, right? There's no curved stuff in there, I don't think, right? Yep. What was your name? Walter. Thank you, Walter. I know 3 names now. I knew 4 names. Nate Dogg, Logan, Riley. Riley, we met each other out there. You met my family. You met my family. One of my kids, and then Walter. Yeah, you guys are all fair game now. All fair game. All right. Let's start this problem. This is a projectile motion problem. This is an odd problem. I don't know when you'd ever have a situation. All these problems are pretty funny, right? Because we're just making them up. We're just making up little exercises for you to do as we go along, right? So in this case, we have we have some sort of say maybe a vehicle down here traveling from left to right, right? And it has it has 10 feet per second, right? And it is accelerating at 2 feet per second squared. So it's traveling to the right there at 10 feet per second with an acceleration at 2 feet per second squared. And then up here, we've got a really weird cannon that has a fixed position. It can't rotate at all. It's a fixed position, but we could change the velocity at which the thing comes out of it, the projectile comes out of it. Okay, just making some weird shit up, right? And so that's what's gonna happen. We're gonna have something, we can change that velocity, and we want that particle from B to strike particle at A, okay? That's what we're doing. And this is a projectile motion problem. We have the gravity coming down. But also note that our initial position here of B is not gonna be 0, it's gonna be 100 feet up there. Okay, and so that's what it is. And there's a 3, 4, 5 triangle. I always love it when I get the 3, 4, 5 triangle because then it's pretty slick. I know many of you go through and you solve for the angle that makes the 3, 4, 5 triangle, and then you go back to the sines and cosines. Don't try not to do that. Try to do it with the little shortcut that we could do along the way. So but it's okay if that's the way your brain works. Do it that way. Okay, so here we are. So how do we know when these things are going to hit each other? What's going to be the same about them? Their positions, right? So ultimately, like I'm thinking, I was like, how am I gonna solve this problem? Well, what I'm gonna do is I'm gonna get the position of B as a function of time and the position of A as a function of time, and I'm gonna set those sons of bitches equal to each other, right? Because then that's what's gonna cause, that's when they're gonna hit each other, is when those positions are the same, right? And then to complicate things a little bit, each one of those particles has an X position and a Y position, right? So we have both of those. So ultimately, I think we're gonna have 4 equations, and we're gonna set 2 of them equal to. You're gonna have the X and Y position of B and the X and Y position of A, and we're gonna set those equal to each other to solve them. I think that's the easiest way to do this one. Okay, so let's at least start. We have 5 minutes. Let's do particle A's to begin with. Particle A. Right. So these are kind of derived the equations before up above, so we could just kind of jump right into using those, right? We got AAX, particle A, we have AAX is equal to 2 feet per second squared, and VAX is equal to 10 feet per second, okay, when it starts out. I'm gonna call this the position. I'm calling it A for whatever reason. I just did that in my solution. I really did it. So the position of A in the X direction is going to be equal to the initial position of A in the X direction plus VA X times time plus AAX times T squared over 2. So I just looked at constant acceleration problems, and that's the equation that tells you what the position is that it's going to be, right? In this particular case, SAX naught is 0, right? I'm going to put this velocity right there, right? And then this acceleration is going right there, right? And so I get SAX is equal to 10t plus 2t squared over 2, okay? That is the position of A in the X direction as a function of time, okay? I'm gonna do the same thing, but I'm gonna do it in the Y direction. SAY. What is the position of A in the Y direction? 0, right? It's just traveling right around there, right across the bottom. It doesn't have any movement in the Y direction. So there's my next equation that I have. SAY is 0. We might be able to get through this. Okay, so we'll do particle B. Particle B. same deal. We got, we'll do the x direction. SBX is equal to SBX naught plus VBX naught times T plus AB, acceleration of B in the x direction times T squared over 2. Okay. In this particular case, right, it is a projectile, right? So it's up in the air like this, and it's being launched to the right. In the x direction, there is no acceleration, right? There's no acceleration in the x direction. There is no initial position in the x direction either. So both these terms are 0. Right? We have acceleration in the y direction, just not in the x direction. So there, and then VBX naught, right? That's the initial velocity in the x direction. And so we look up here, right? And we've got that velocity coming down, and I want the x direction of it. And what's really nice about the 345, right, is it's going to be 4 over 5 times v naught, right? Because you just, all you do when you get to here, you just say, oh, it's this guy, right? The horizontal direction over the hypotenuse. So it's just 4/5 is what it ends up being. So this guy is 4/5 v naught. 4/5 v naught, right? Because it's the horizontal components. You just grab the 4. That's a lot nicer than trying to calculate the angle that gives you that same triangle and then using the sine of it. And then if you did take this, or the cosine of it in this case, if you did do that and then find the cosine of it, you would find that the cosine was 4/5 is what it would end up being. And so it's just it's kind of a roundabout way. But if that's the only way you want to do it, and it's in an exam, and you're panicking, just do it the way, just keep going with the way it is. But try to learn this way. I try to use those types of triangles to make your life easier, right? And so let me just write this equation, and then we'll finish this next time. This is SB x as a function of time is equal to 4/5 v naught times time. That's it. And you're like, oh, wouldn't that be good if we would have had time to finish that problem? But then you wouldn't have heard the story about Netflix and flat earthers. So I'm well aware that my sidetracks sometimes throw us off a little bit. But we'll just finish this one next time, right? And then we'll do another quick one. It's kind of different, where you start out with the positions and you go back to accelerations and velocities, which is kind of backwards. And then we'll do everybody's favorite angular momentum. We'll do polar and cylindrical coordinates and normal tangent.